Hey everyone, let's dive into the fascinating world of quantum optics, a place where light isn't just light, but a field of photons with mind-bending properties. Today, we're peeling back the classical layers and exploring what an optical image really is at the quantum level. In classical optics, an image is just a mapping of light intensity from an object to a screen or sensor. It's pretty straightforward. Rays bounce or bend, and a pattern of brightness appears. But when we zoom in to the quantum level, things get a lot more interesting. Light isn't a continuous wave or a collection of rays, it's a quantized electromagnetic field made of photons, each described by a wave function. Now let's talk about the photon's wave function. A single photon doesn't have a defined path. It exists in a superposition of all possible paths. The wave function describes the probability of detecting the photon at any point in space. Instead of light rays forming an image, you get a probabilistic field. The optical image emerges as many photons collapse their wave functions at the detector one at a time. But there's more. Photons interfere with each other and with themselves, creating the fine structure of an optical image. Think diffraction patterns or the airy disk of a focused spot. In quantum optics, we describe these light fields using the coherence function and higher-order correlations which show how detection events at different locations are related. These correlations define contrast, sharpness, and resolution in a quantum image. Now let's get exotic. In systems using entangled photons like spontaneous parametric down conversion, you can create images in ways that defy classical logic. For instance, ghost imaging allows you to form an image of an object without detecting any photons that interacted with it. One entangled photon hits the object while the other goes to a camera. The correlations between them reconstruct the image. Cool, right? And then there's subshot noise imaging. Using entangled or squeezed light, you can image with lower noise than classical limits. And super resolution techniques using quantum correlations can push past the diffraction limit. At the deepest level, we describe quantum optical images using quantum field theory and operators. Light is a quantum field, and we use operators like the photon creation operator and the annihilation operator. The density matrix describes the quantum state of the light field, and from this we can calculate all imaging properties like contrast, spatial resolution, and quantum noise. So what is an optical image? It's not a static object. It's a statistical record of many quantum events. Each detection is a collapse of a photon's wave function. The final image builds up over time by detecting many photons. What we see is really the ensemble average of quantum measurement outcomes. Send just one photon through, and you get a point. Send many, and the interference and probability distribution reveal the image. That's the quantum view of an optical image. Mind-blowing, isn't it? Thanks for watching, and stay curious.